Hello, AP Stats. All right, here we go. We're looking at 2.2, Describing Variability. And we've already done a lot of this stuff, but it bears repeating. Okay, let's take a look at why we need to describe variability and do it in a little more detailed way than we have so far. So far, we've really just talked about, we've done a lot of standard deviation. That's what we're getting to today. But we've really just talked about finding our spread, which is the distance from the min to the max, right? This, okay? Usually done in that notation right there, okay? And then the range, 50. So if we take a look at these three sets of data plotted on these graphs here, okay, we can see this one's nice and spread out, but we have the spread of 20 to 70 and the range of 50, okay? This has the mean of 45, and if there's a dot right here, then these all have a median of 45 as well. But they're very clearly three different pieces of information, or three different data sets. Okay, so taking a look at this one, very different, right? We've got this cluster right here and these outliers right here. But still, we have a spread of 20 to 70, a range of 50, and a midpoint there of 45, or a middle of 45. Okay, down here, tighten things up a little bit. Okay, the spread is really small compared to the others, just a range of 10 from 40 to 50, right? But the midpoint will still be about 45. Anyway, we're going to need to have some more vocabulary around this, and we're going to use what's called a standard deviation to talk about the average distance from the mean of any particular data set. Okay, so we need to talk more about variability beyond just the spread and the range. Okay, so what we're going to use in statistics is called a standard deviation. Okay, and we're going to talk about how to lead up to that. So here we go. Okay, the first thing is, what is a deviation? Deviation is just you take a data set and you subtract it from the mean. That's the deviation of that data set. So we're going to take a look at this example, some fast food stuff, talking about calories or something from French fries. Okay, so I've taken this data right here and I found the mean, which is 287.714. The median, which we're not really going to use, but I always like to see it, right? 270. And our number of data points is 7. Okay. Now to find the deviation for this data set, we are going to take each data set and subtract it from the mean. Okay. That gives us the distance from the mean that each data set is. Okay, so we did that all the way down here. Data set subtracted from the mean. Data set subtracted from the mean. On and on and on. Right here. Now, if we found the average of these numbers, right, you would add all those up. The sum here is 0.03. So add all those up and divide by 7. And we get basically 0, right? I mean, that's not describing the distance from the mean, right? Even though it's the average deviation. So what we have is what's called a standard deviation. And the problem with this whole scenario is these negatives, right? Okay, distance is usually not marked in negatives. So what we do is we actually square this and then take the square root of it, and that's our standard deviation. But variance is when we have this sum all squared. So what we do is we take a data set, subtract it from the mean, and square it. Okay, and we add all those up. That means the sum of all of those. Okay, we divide it by n minus 1. That's when it is a sample variance. If it was just a variance, we just divide it by n. Okay, a population variance, we divide it by n. Most of the time in this class, we're dealing with samples. We're going to divide by n minus 1. Okay, we'll get a sample standard deviation, and that is simply the square root of this. So we just get rid of that squared by square rooting both sides, and we take the positive side of that. Okay, so the French fry example again, and we're going to calculate the sample variance and the sample standard deviation. Sample variance is just squaring each of those differences that we got, right? All those squareds, and then adding all those up and dividing by n minus 1. So when I added all those up, I got 75,611.429. Okay, divide that by 6, got 12,601.905. And so that is my sample variance right there. Okay, this sample standard deviation, denoted by S, is just simply the square root of that. Okay, which is 112.258. And that is, okay, and here's the definition of standard deviation: the size of the typical deviation from the mean. Okay, so what I usually say is the average deviation from the mean. Okay, average deviation from the mean is a decent definition of what a standard deviation is. Okay. If you're measuring the entire population, we'll use this sigma. Okay, we'll use the Greek if we're using entire population, sigma. We will almost all the time be using samples, and we'll use just an S. God, get rid of that. Okay, so let's take a look at this back-to-back stem plot and talk about the data we have. Okay, so what I would do right here is I'm given this back-to-back stem plot, and I'm asked to kind of do this stuff. So what I go first to is, what am I asked to find? I'm asked to find the mean, the range, and the variance. As soon as I see this variance, I'm definitely going into L1, putting this data in, and then writing down what I have. Okay, so I go to L1, put this data in, I get a sample mean there, I get my spread there, I get my range there, and the variance there. Variance, sample variance, make sure we're using sample variance, okay, is the S squared, okay, right there. Then I go into L1, punch this in, get the information here, and I take a look at it. And I see the means are different, the spreads are different, the ranges are the same, and the sample variances are the same. So I'm looking at here and say the same range and same sample variance, so the answer is D. Good. Take a look at this. It's kind of interesting, talking about resistant and non-resistant. We'll take a look at how this works. Okay, so we have a sample of 20 employees' salaries from a large company with the following salaries. Okay, so, and these are in thousands of dollars. Okay, so all these people make this much money. Boom, boom, boom. Okay. Suppose the company's employees receive a $3,000 raise for next year. So everyone across the board gets a $3,000 range. The standard deviation of the employees will not change. It would be unchanged, because if you add it to everything, the difference will not change, right? The difference from the mean would not change, because the mean would jump up and everything would jump up. But if we gave employees a percentage raise, like what normally happens, right? We get a 25% raise. That would be an awesome raise. Anyway, that would affect the standard deviation by 25%. So we would take the standard deviation of 14.75, multiply it by 1.25, that's a raise of 25%, and we'd have a new standard deviation of 18.438. Okay. Going back to some of the information we see in the 1 VARs, right, is our quartiles. Lower quartile is the first quartile, upper quartile is the third quartile, okay? And the IQR is the distance between the lower and the upper. And it is a resistant measure of variability. Okay, that's going to be important to figure out what is resistant and non-resistant measures of center and variability. Okay, so we have this whole question here. You can throw that in 1 VARs, in L1, and do a 1 VARs and get all what you need right here. We're not going to walk through that tonight. Okay, last thing we're going to do, I believe, yeah, I think this is the last thing we're going to do. Yes, okay. So the last thing we're going to do here is we're going to talk about a couple last things we're going to do. Let me get where I need to go. Okay, so the last thing we have here, okay, what is another name for the second quartile? Well, it's the median, okay? Why is an IQR considered to be a resistance statistic? Because resistance statistic is the definition. The definition of that is adding extreme observations will have a little effect on it. And when the best place to look at an IQR are these box plots that we covered. Okay, if we added something out here, it wouldn't change this whole thing. It wouldn't send it off to the side. Okay, because again, this is the median, not the mean, right there. Median right there. Okay. So it has resistance statistics in it. Okay, we are going to take a look at this and see if we have any outliers. I want to go over this again. Okay, so I throw all this information into L1, okay, and I'll just give you the numbers, okay. So we have, let's see here. They give us Q1, right? The Q1 is 234, and the Q3 is 298. Okay, so the first thing we're going to do is find the IQR, right? 1 IQR, and that equals Q3 298 minus 234. So the IQR is 64. Now, if we remember, hopefully we do, when we're trying to find outliers, we need to find the IQR times 1.5. So that equals 64 times 1.5, and that equals 96. Okay, so that is our IQR times 1.5. Now, what do we do with that to find our outliers? Well, here's what I like to do. I'm going to go Q1 minus the 96, and then Q3 plus the 96. So we have Q1 was 234. We subtract 96 from that. Q3 was 298, and we're going to add 96 to that. And so we get what I like to call our safety zone. That is in between 138 and 394. Good. Okay, so the question is, how many data points are outliers? Okay, so we're looking for really small, really big. Okay, so I'm going to get my highlighter out, and I'm going to look around. I'm going to look for anything. Well, I see it right away. Boom, 129 right there. Okay, and then looking for anything above. Okay, I'm looking for 400s. I see 1, 2, any in the 390s that I got to be aware of. I don't think so. I don't see any more. Okay, so I gave it a good once over, okay, and I see that there are 3 outliers. All right, that'll be it for today. Go ahead and get that homework done, and we will see you on Monday. Have a great weekend.